Hey folks, it's Jeremy. I've been thinking a lot lately about the importance of kids making connections in mathematics, and I've been working on a framework to help teachers and instructional leaders understand how kids make those connections and why they matter in math. Uh, be able to get to that framework, which we'll talk about in a moment, I wanted to start off with something really important in framing all of this is that we have some goals, right? So let's think about the goals that we have when we're teaching math conceptually and for understanding. There are a few, right? The first is that we want kids to be making sense or making meaning, right? On a regular basis, right? It's the kind of classroom that we want. We want kids to know what they're doing and why they're doing it. Things that they are doing should make sense, right? Not just procedures that don't. That's one goal that we have for teaching math conceptually. We also want to promote critical thinking. Now, critical thinking is very related to making sense, but it also ups the ante a little bit in not just understanding what you're doing and why you're doing it, but also thinking critically when you approach a task or an assignment or a math problem or mathematical situation in life. You want to critically think so that you select the right strategies or right references even that they're going to use to solve a problem, right? So we want kids critically thinking. That's one of our biggest goals. And then lastly, we want kids to make rich connections, right? Those are connections between types of mathematics or science or other areas that they might see math used, but it's also connections to applications, right? So thinking about when they might use a specific type of mathematics, right? So it's more than just one connection. It's a connection within and across and outside of mathematics. Now, the big goal of all of this, right, that we're trying to do is get kids to sort of apply in a lifelong manner the things that they learn in school, right? Things should make sense. We should critically think about them and they should make connections, but not just in school, but out of school. That's why we're learning mathematics, right? It's not just learning for academic sake, but we know that that's important as well for students, all students, right? To be able to achieve. So we're asking, our big goals, right? What are they? Well, it's for kids to apply what they learn in school and to achieve at the highest level that they're capable of. And we know that all kids are capable of achieving at high levels in math. Now, the question that we have to ask ourselves after we've set these really big pie in the sky goals is how can we achieve those goals, right? There's a great book called Standards-Based Math Instruction. It's a case book for professional development. It's authored by Mary Kay Stein and a few other authors as well. And they have a particularly useful framework for thinking about how you might reach goals, right? And one of the things that we know from other research, not just theirs, is that to reach goals, right, to achieve at a high level, right, to really learn in the long term and retain what you're learning, is that kids and adults, frankly, need to engage with cognitively demanding tasks. And that same thing is true about mathematics in particular. You have to be pushed to think at a high level and apply and think outside of the box with what you've learned to be able to achieve at the highest level in mathematics. And that's why curriculum should always be rigorous, right? That it's not just a regular word that we use to describe something that's hard. It's actually that it's cognitively demanding in very specific ways. So their book does a great job of outlining this idea of cognitive demand, and they include a framework in their book that's very helpful. At the lowest level, and you might find this familiar, right, or related to Bloom's taxonomy, but at the lowest level of cognitive demand, there are tasks that require memorization. Now, I'll give you an example of these in just a few minutes, but memorization is quite literally this idea of repeating or regurgitating or just recalling information without applying it, right? It's not conceptual. You're basically recalling a definition, right? It's not necessarily that memorization is bad. It's just that is the lowest cognitive demand in the framework of tasks that students might get, right? So it's recalling definitions, right? Or formulas or procedures, right? So recalling them. right? Recall only, right? It is not rigorous, right? It's not demanding. At level 2, which is still lower demand in this framework, is procedures without connections, right? So procedures, mathematical procedures without connections. Now that quite literally is following a set of predetermined steps, right, in order to solve a problem. It's an algorithm, right? So we'll call that algorithmic thinking. And almost by definition, there's one way to do it. And this piece right here is really important, right? Which is procedures without connections means also that the task itself, as it's posed, does not require the student to make connections to other types of mathematics or to explain why what they're doing works, right? So that is procedures without connections. At a higher level of cognitive demand, right, we have a couple of other examples here, a couple other types of tasks. This is level 3, which is the second to highest level, which is procedures with connections. And procedures with connections is exactly what it sounds like. It basically requires you to use a procedure, right? Whether that's dictated or you dictate which procedure you're going to use. But the task requires you to make a connection to another type of mathematics, either by explaining your thinking or finding the solution in a different way, right? So it is not, by definition, it is not algorithmic only, right? It requires you to actually show that you understand the procedure that you're doing by solving it or explaining it in a different way, right? In that way, it is conceptual because it requires you to make a connection that was not dictated to you, or to provide a proof, right, for the procedure that you used, right, using a specific set of criteria, which I'll give you a moment, right? You use that procedure basically to find a connection, right? And then the highest level of cognitive demand is doing mathematics. Right? Now remember, we're talking about the tasks themselves, right? And what those tasks require. A procedures with connections task requires you, or asks, right, to solve the problem in a specific way, but then also asks you to solve it in another way or to explain it in another way, right? Where a doing mathematics tasks, right, simply states the criteria that you need to meet, but it does not tell you how to solve. So in that way, it is also non-algorithmic, but it does not suggest a pathway or a procedure. Whereas this, it does have a procedural requirement. So those are the 4 different levels. Let me give you a quick example of each level. So for example, at a level 1, the question might be, what's the formula for area, right? The requirement or the demand of that is to simply state that area equals length times width, right? So it's not necessarily a bad thing to know that. It's a great thing, actually. But the task itself is just asking you to re-say, right, or recall a formula, right? At a level 2, let's give an example of a related task, right? If it just simply said, if the task said, calculate the area of a 7 by 2 centimeter rectangle, right? And in particular, if the numbers were stacked up like this, that task is actually just asking you to find the answer, right? You could use an algorithm to solve it. There's no expectation that you use proof or another method to find it. Let me now give you an example of a procedures with connections task that's related. So now we're at the higher level of cognitive demand, and they might say something like, hey, given a specific area, right? So you might say that the area is 36 square feet. Give me 3 different rectangles, the dimensions of 3 different rectangles, right, that might have that same area, right? And then explain how you found each of those areas and why the area can be the same, but the dimensions might differ, right? So it tells you what to do. It says, hey, here's a given area. Find 3 rectangles, right, and share the dimensions that could be that area, right, or could be a rectangle with that area, right? And that is a procedure, but it asks you to make a connection, right? Because it's requiring you to actually tell how what's the connection and why they can have the same area but different perimeters, for example, right, or different dimensions, right? Now, at the highest level, doing mathematics, you might have like no requirements, right? But you actually might need to provide proof or cases as examples for a given problem, right? So, how many different whole number dimensions can a 24 square foot rectangle have, right? How does the perimeter change in each of these rectangles, and what is the relationship between area and perimeter, right? So now all of a sudden it didn't tell you to make a certain amount. It didn't tell you to explain a specific thing. It's actually just setting a large, broad criteria, right, for a very challenging and cognitively demanding task. So now that we know that there are higher and lower demand tasks, it can help us think about the importance of connection making in mathematics. Now, what I'm about to speak about is not just about connection making for students, right? The requirement that students make connections, but also the importance of teachers eliciting those connections in their instruction, right? So, thinking about operating up here as much as possible because we want to be able to reach these big goals that we have, right? So I want to share a bit of an example about what I mean about the different types of connections that kids can make in mathematics. Now I'm going to go across this framework here that I've developed, and there's this idea that math, right, can be shown in different models or different types or different modes, right? So I argue that you can say that you can show math in a concrete manner, a graphical or pictorial manner, right? You can express mathematics in a verbal manner, and then you can express mathematics, of course, as number and algebra. So let's actually talk a little bit about a problem, right? That might be a common problem. It could be a procedures with connections or doing mathematics problems that is going to require you to make connections across different types of mathematics. So let's think about 2 people are sharing 3 brownies, right? So let's just say 2 people. They share 3 brownies. And our question here is, how many will each person get? Right, so that's our question there. I'm just going to partition that off. So that question, right, is asking something very particular, but when we start to think about the different models or types of mathematics that you might be able to demonstrate this task in or using, we're going to go across those models, right? So concretely, I'm not going to cut up brownies right now for you, but let's think about actually physically doing this task and how a student might actually be able to answer this question and to show that they understood what they were doing, right? So let's think about it for a second. We've got 2 people. Let's say these 2 people are actually physically standing there, And we have a couple of real life brownies that we could manipulate, right, using a kitchen knife. Now let's just pretend that these two brownies are the same size and they're sharing 3, right? So the physical proof, right, or the physical way or model for solving this problem could potentially be that, we take this first brownie and we give it to this child, right? So this child has 1 brownie. We take the next brownie, we give it to this child. This child has 1 brownie. And then in this case, right, we would physically take a knife, right, and then cut through this brownie, right, so that we ended up with 1/2 for each of them, right? So you could actually see that the individual physically got 1.5 brownies, right? So we've answered our question with a physical model, right? Now, a graphic or pictorial model can take many forms as far as sophistication, but let's just show it in a super basic way. So we can use drawings, and students often do this. And in a problem like this, the drawing might actually mimic the actual scenario, right, that we went to. We use a slightly different strategy here so that we can see the nuance. But in this case, let's say that the child coordinated the amount of a brownie that a kid might get if 2 were sharing 3 initially. So knowing that, they might say, okay, person A and person B, if I cut each of these in half, since there's 2 of them, I'll know that when I get down to the end of the brownies that it would have been fair shares for everybody, right? So in this picture, right, this model, this graphical model of the situation, right, this half of the brownie goes to person A, this half of the brownie goes to person A also, and this half goes to person A as well. The same thing would happen for person B. And when we look at those, that is 3 halves, or 1.5 brownies per person. So we have a graphical model, right, that really mimicked the physical model in this case. But that is another separate type of proof, right, for the answer, right, in this case, right, which is 1.5 brownies. Now, verbally, a student might be able to actually use logic to explain. It'll relate closely to what we just saw, but they might say something, right, that each child is going to get 1 whole brownie. The remaining brownie can be split into 2 equal pieces, so each child gets 1.5, right? So I'm going to do shorthand for that, but each child can have 1 whole brownie and 1/2 brownie. Now we get into number and algebra, and the possibilities really are really extensive. But what's really important for us to think about here, right, is how these might connect to each other, right? So we'll get to that in a moment, but let me think about that for 1 second. So we'll start sort of modeling what happened here, right? Which is we have 1/2 plus 1/2 plus 1/2 equals 1 and 1/2, right? That sort of models what's happening there. And if we did this twice, right, we would be able to get back to a total, all right? Even though our answer is here. So that's one way of thinking about it, right? We also could go back in and think about what operation most closely matches this, right? So 3 divided by 2 is going to get us 1.5 as well. And if we start to think about it in a way that might look a little bit more like a ratio, and I'm going to come back here and draw a picture of it. just to illustrate what we're talking about. 3 equal sized brownies. You have person A and person B sharing them. If we look at the proportional relationship between, or across these, excuse me, that's not quite straight, you can actually visually see that the equal line, so the dividing line or line of symmetry in this case would leave an equal proportion on both sides, right? So it's 1.5. So if we think about that, there's 3 brownies for every 2 people, right? And if we solve that ratio, right, we're going to get 1.5 or 1.5, right? Now, if you think about what is generalizable about this idea, right, is that fractions are division, right? So if we think about this idea of B divided by C is equal to B over C, right? Now, the real magic that comes in all of this, right, when we're thinking about our goals and keeping our tasks at a high level of cognitive demand, is that the real understanding comes across a class of students when a child is able to make a connection between different types or models of math. So if I'm a student and I were able to solve the problem, let's look here. If I were able to solve the problem this way, that is a relatively straightforward level of understanding. Now, if I'm able to also connect this, right, to an equation that shows that I also know what I'm doing with number, right, then I, as a teacher and evaluator of this student, right, know that this child understands deeply, that they're making sense of the problem, that they're critically thinking, and that they're making connections, because they're displaying it across more than one model of math, right? Now, let's think about it on the teaching side, right? So if the child does those 2 things, right, puts this model together with this model, I'm pretty darn satisfied that the child knows what they're doing. Now, if they could add another model to it, right, which is a written explanation that explains their work, I'm over the moon, right? Because I know that child is really applying what they understand and using the math. They're actually doing mathematics, right? Now, from a teaching lens, this idea of making connections is very much your friend, right? It's a real tool for helping students understand and make connections if they're only operating at one level. So imagine a student who is operating at this level, right, can only work concretely with a manipulative or with an actual brownie to be able to solve this problem, but they haven't yet been able to abstract towards a graphical representation, a verbal representation, or a number or algebraic representation, right? So let me just shift this a little bit so you can see the full model. Excuse me. And what we want to do is sort of think about the ways that teachers might model the mathematics, right, or make connections or ask questions that require students to make connections to provide access, right, to multiple students in the room. So imagine a child is operating just at this level right here of concrete, right? A teacher might be able to have this student come up and share or demonstrate in front of the class first, right? So let's say that this is student 1, right? If the student then shares their thinking, sits back down, and the teacher asks them and the rest of the class to see this student who might have modeled it this way. Let's do that. We'll call that student 2. If this student comes up and then says, well, I drew a picture of both brownies, right? And I saw that when I lined the brownies up, that if I drew a line right down in the half, that on each side of those, right, which represents the 2 people, the 2 sides, each person gets 1.5 brownies, right? And so that's just like person 1's strategy in many ways, but the teacher should be asking the students, right, how is that similar or different to the way that child 1 solved it, right? Now, as we become a little bit more sophisticated, right, in this, we can layer another strategy on it. So let's look at this, or another model, excuse me. So if we said that student 3 was the third person to come up and share the way that they solved it, that student might say, well, I use numbers, right, to solve it, right? 3 divided by 2 equals 1.5. Now that's just an equation, that's not much of an explanation. But if that child were to say, right, that multiplication and division are inverse operations, and so whenever I'm thinking about, 3 divided by 2 equals something, I can ask myself a missing factor question, all right? What is it that multiplies twice to give you a total of 3, right? So that child might say 1.5 times 2 is equal to 3. Therefore, 3 divided by 2 is equal to 1.5. So if we're in that classroom and the teacher then says that same question again, all right, so how is child 3's strategy connected to child 2 and child 1? So hopefully what we can say then, or we can have kids say, is the explicit connection between the numeric model, the graphical model, and the physical model, the concrete model. And so in this case, the child might be able to say something like, well, this literally looks like 3, then 1, 2, 3 units, right, that are divided equally into 2 parts. Here's 1 and 2, right? And on each side of that, I have 1 1/2 brownies, right? And if we were going to think about the math in there, right, as it related, we know that if we work backwards, right, that 1 1/2 times 2 equals 3, right? So our answer must be this missing factor here, right? So I encourage you when you're teaching, right, to ask questions that ask students to make connections across the different models of mathematics. And I also encourage you to require your students not just to engage in cognitively demanding tasks, but to also to be sure that those tasks demand that they make connections between different types of mathematics. And the reason why that matters, not just in school to reach these goals, but also in the field of mathematics, is because that's basically what a proof is, right? You have to prove that your strategy and answer or solution work by including some other connection to another type of mathematics that proves it, right? So thanks for listening, and go get them in your classrooms making those connections. Bye.